Cool. You want to kick it off, Aparna?
Yeah. Happy to. Okay. All right, guys, I have some fun Excalibur visuals drawn up to explain this one. So hopefully you're in the mood for that this Friday. Okay. So this paper was actually posted by Harrison in our Slack community, and it's a really good one. So thought we'd go over it. Let me just start sharing my screen. So this is actually from OpenAI. And I loved, by the way, anyone else who read this paper, this is so cool compared to just a PDF. It was actually interactive, and you could go click on it and actually see the simulations and what they did. So I hope they do more of these in the future. This was really cool. So basically what they tried to do here is, if you think about like the high level summary, felt like, how do we explain large language models? And the world of the past, where people were using SHAP and all these approaches, what does that look like for LLMs? Was really what they were starting to explore with this paper. And what I'll do is maybe go through first just the steps, and feel free to chime in if you guys, those of you who've read the paper feel like there's other things you'd add. But maybe we'll just first go through what their algorithm was for this explanation, and then we can go through the results and where do we think this approach works, what's the limitations of it, and talk through that.
What do you think? I guess maybe at the beginning is what do you think the end goal of this is? And what would be what would be maybe ideal? What does the SHAP world look like? What are they trying to do here?
I think one of the things for me is that most people today still don't know. And how many times have you guys had a conversation like, wow, this is so good. Like these LLMs are so good at answering questions. They're so freaking smart, but you have no idea why. You have no idea how you would then go and make it better. And so for me, part of what's cool about this work is that you might first have a way to actually explain the reasoning. Why did it give an answer? And then the ideal hope for me is that it can then help you understand how to make it better. So similar to maybe in the world of SHAP, where you look at what were your top features, what's working, what are features that aren't really doing much. In this case, is there a way that, when there's hallucinations or there's infactual responses, is there ways to go back and figure out, I don't know, specifically what neurons or where could you go and improve to get better responses? So that was it for me.
Yeah, I think that's a good take. Like the more you understand something, the more you might be able to control it, the more you might be able to understand what it's doing even from a monitoring or observability perspective, the more you might be able to improve it. And so this is, a take at interpretability, trying to apply AI to understand AI.
Yep. Okay, let me jump in and I can start explaining the algorithm. So they walked through a couple steps of what their technique was to explain. First was, so let's say this is so high level, they are using GPT-4 to explain GPT-2. GPT-4 is the explainer model. And what they're doing here is, for each, call it neuron, they take a specific neuron, they're giving it some text, and then they look at, well, what text was the neuron activated on? Like what token words or what keywords did the neuron light up on? And they do a first pass of this using, call it, I'm going to jump into my Excalibur visuals here, but they have the actual neurons from the GPT-2 model. And they do a first pass where they just understand, well, what words does it light up on? And GPT-4 gives an explanation saying this neuron is activating on, in this case, numbers, ordinal terms, and possessive constructions. So that's what this neuron 1 gets highlighted on. Then what they do for step 2 is they then simulate activations using GPT-4 on the explanation. So you have these actual neurons, you've generated an explanation, and now you create simulated neurons. Let me explain that one more time. So there's actual neurons from GPT-4. First, it figures out if this is neuron 1 represents whatever they said it represented here, right? So it represented numbers, ordinal terms, possessive constructions. It has an explanation. This is done by GPT-4. Then, based off of that explanation, it simulates a neuron to actually it simulates a neuron to just based off of that explanation. Anyone with me so far? Any questions on this?
And it simulates that the sentence activations based upon the explanation.
Yes. So if it generated a summary like, there's a better example down below, actually. Okay, let's do this one. So here, assuming that the neuron activates on, this is the explanation. It goes ahead, it generates a simulated neuron, and then it compares the score between the real neuron and then the simulated neuron. And it figures out how close is the neuron that was simulated matching up to the real neuron and the tokens that the real neuron actually got activated on. So you're then generating a score to compare actual neuron versus simulated neuron. And big picture, why are they doing this? Like, why am I generating an explanation and then going and generating a neuron? Well, what we're trying to do is figure out first, well, if we think, let's say neuron 1 over here, if we think neuron 1 is about, let's say dogs, like let's say neuron 1's about dogs. And that's call it our hypothesis, right? Neuron 1, it's everything related to dogs, it lights up. Well, based off of that, we can go and simulate, here's this, if that's what we think it is, here's this simulated neuron 1, it should also light up on dogs. And when you then go in and you compare, you have a block of text, let's call this the real neuron, you call this the simulated neuron, you would hope that both of them, anytime that this block of text mentions dog in this text, both of them would light up. So both of these would kind of light up. And if the real one does, but the simulated one doesn't, or the simulated one does, but the real one doesn't, then the simulated neuron doesn't actually capture the essence of what the actual neuron represents. So what you'd ideally want is for your simulated neuron to capture the essence of what this neuron's about. And if it doesn't, then it's not really a good explanation of this actual neuron. Does that make sense? And if it doesn't, I don't know. So someone say it doesn't, so we can dig in here. Because this is like, I think the first time I read through this, I was like, this felt really complicated to just explain, what it's doing, but it actually makes sense. I feel like the second pass of the paper. Yeah, go
It'd be
ahead.
good to, like, I think they give some good examples of prompts in the of like the prompts that actually create these. If you go down right here.
Yes. Yeah, let's go through an example of this. So first, this is step 1 again. This is the part where it's generating explanations of the neuron's behavior. So it's like this part of the workflow. And what it does, it's saying, okay, we're studying neurons in a neural network. It first gives it a few prompts, so kind of few shot learning, to kind of learn what the format, what it should be doing. So let's go through. In this case over here, this is token words. These are the words that it lights up on. In this case, together, nest, town. Anyone want to take a guess? What do you think that this neuron's focused on?
Maybe community.
Community, yeah.
Yeah, okay, yeah. So if you had to do a summary of neuron 1, you might say it's community, and you will be right. So it is community. So that's kind of what this first part is doing.
What was the prompt? So what was the question being asked? Like, what is the question you're asking in this area, and what is the right answer?
Sorry, ask that again.
Yeah, what's the prompt? Like, what's the prompt? So this is kind of a one-shot example. What's the actual prompt being asked, and what's the actual?
Yes, so the prompt is look at the parts of the document the neuron activates for and summarize in a single sentence what the neuron's looking for. And it gives an example like this. Here's tokens, here's the activation, and based off of what it's asking is based off of what it got activated on, give me an explanation of what that could mean. Yeah, go ahead, Aman.
What is there a reason why the nest part seems to have a high number of tokens? Like nest has 7? That's kind of weird, right? Like
A high activation for that token, you mean?
yeah.
That's what I was thinking too, is like, why did it fire on Ness? Like, why is
Is
that
it
higher?
like togetherness, strong? Is it like a suffix that it's capturing?
Is it like, yeah, is it like weighted by the previous token? Is that what drives the next token's weight? And that's why like the following token together would be Ness, or
Yeah, I mean, so these activations can, or because of attention, a single token or a single neuron can actually be driven by it could have influence from the previous token and the next token. And they talk about it later in the paper that some of these neurons are actually more predictive of the next token when you're looking at a specific token. So yeah, so there could, I think the activations will be content centric.
I was thinking about other words that end with nest, and I couldn't think of any. Just to see if there's, like
Closeness. Like
yeah. Yeah, okay, that's a good one, Jamie. Yeah, maybe all the words.
Happiness.
Yeah.
sadness.
So each of these words given a score, and then that score. So using that, it comes up with the summary of the main thing this neuron does is find phrases related to community. So this is an example. They did this for neuron 1, and then they asked it to go do it for, let's say, neuron 4. And the words there was escaping the studio, pick, call, is warmly affecting. Yeah, so that's kind of the next phrase set here. And neuron 4 looks like it highlighted on 9 for aping the and then affecting. So this is what this was activated on. And then it asks, okay, explanation of neuron 4 behavior. The main thing this neuron does is find blank. So it's asking GPT-4 to go explain what neuron 4's behavior is. Anyone want to take a guess at what neuron 4's summary explanation is?
That's a tough one.
Yeah.
What the heck is it aping?
I have no idea. I think it's the ending part of it's escaping.
I mean, I don't know if I trust this. I'm gonna be really honest.
I don't like, so I have a couple hot takes.
Yeah.
And I was gonna save them for the end, but like it is a very
Pretty
rough.
novel. Yeah.
And I actually, God, I was gonna save this for the end. One of my hot takes is like neuron by neuron, trying to understand these is probably a tough lost cause, but let's keep going, because I think you need to get there yourself. But
Well,
my other hot take, if you look back at the first one you just went through, Aparna,
yeah,
is like, if you think of the stuff we do in CHAP and in the statistical space for NLP specifically, it's like statistically what's activated and kind of gives you the, you know,
yeah,
gives you the attribution across your words based upon the sentence coming in. And it's kind of a mixture of that plus a bit of an explanation. So if I take those words that it was activated on, let me use GPT-4 to give me like a real explanation. So it's a little bit of a mix of those, kind of, you know, on top of each other is kind of what this felt like to me.
But
yeah,
like, don't you feel that like the way the architecture of transform, like the whole, like a large language model is so complex that looking at it on a neuron level is like too univariate, in my opinion. It's like so novel here. It's like, it's kind of a cool idea, but I don't think this scales up to like larger context links. Like I just don't think, I don't know. It's super
Yeah.
novel, super cool, but like I don't think it works to be.
I probably have the same take as that. Like, but the most interesting thing is when you have like you can look at our embeddings, which are multiple neurons activating at once, and many times they work together. Like looking at just one in isolation is one of the big misses of this, it feels like to me, because they can all work together to define something. We're just looking at one at a time is tough. Do you want to go to the simulation portion, like
yes,
the one
yes.
above?
You guys are jumping ahead in the paper.
Yeah, sorry.
Limitations.
Well,
Let's
the other prompts were pretty good. Yeah.
yeah. So okay, so let's just go back to first understanding what this does, and then we can rip it to shreds. But let's let's figure out what it does first. So the summary of neuron 4 that we just looked at, I thought this was really bad, but the summary that it came up with, by the way, was the main thing that this neuron does is find present tense verbs ending in ing. So that, because, you know, you saw aping ends in ing, affecting ends in ing. So GPT-4 thought that this neuron in GPT-2 was focused on finding, it activated on ing verbs. So what it first does, so we've talked through this part, right? So now you have examples where it took an actual neuron. So number 1 here was actually, what was it? It was what did we say? It was community. That was the explanation that it gave. Number 4, this neuron, it said, was ing verbs. Like that's what it thinks this one's about. Next, what it does is it tries to simulate the neuron's behavior using the explanations it just made. So in neuron 1, the explanation was the main thing this neuron does is find phrases related to community. Neuron 4, present tense verbs ending in ing. And it goes through and it actually tries to simulate. It uses, call it the simulator model, to simulate neuron activations for each subject model token, conditional on the proposed explanation. So in this case, it uses GPT-4, which is a simulator model, to then go and simulate activations on these tokens.
So basically this example is the main thing the neuron does is find phrases related to community, assuming that what would be the activations on the tokens, and so that would be the prediction. That would be, this is the one-shot example of what the output of the model should be. Is that right?
Yes.
Okay.
Yes. The thing that I still am not totally clear on this is, does it just go back through the same data points and generate that? It's probably later in the paper, but, or does it look at new documents and then generate the, I don't know if anyone else who read the paper can answer that, but yeah, go ahead.
Yeah, you're talking about like so they simulate on the training. So a lot of this is on the training data about the set. So they go, so these examples, that they
It's in
test
the-
against are actually from the training data.
Got it. So it just goes back to the same training data set.
Yeah.
Got it. Okay. Interesting. So then it comes up with the, let's just go to the scoring part here. So what it's doing in step 2 is it's generating these, call it simulated neurons, is kind of the best way to think about it, where it goes and it's like, well, this is what it should be activating on based off of this explanation. So this is what it should be scoring. And then what it does is it uses step 3 in the scoring. It's comparing the simulated neuron behavior with the actual neuron behavior. And so they take the same, call it document. I felt like this one up here was a little bit easier to see, but it takes the same document or the same piece of text. It has the real neurons, it has the simulated neurons, and then it tries to match up where did the simulated neurons and the real neurons match, and it gives it a score of how closely they match.
And that one's pretty bad.
Yes. And you could look at different neurons. So I'm looking at selecting a neuron. This one's, the explanation was language related to Marvel comics, movies, characters. And this one's a little bit better, 33%, it looks like. And so there's a couple different examples of doing things right. So they both highlight on correctly. Yeah, I don't know. This one highlights on lake. So you can go and you can look at kind of different examples and see how closely is the real versus the simulated. And you get these set of scores. And what it's doing here, let's take a look at this one over here. It's actually comparing, and we'll talk through random only versus top, but it's going through and then it's looking at the correlation scores between the real and the simulated.
And it's worth noting, going back to the scoring, this is probably gonna be another rip on the paper, but apparently they only found 1,000 neurons in the entire set. Or there's 1,000 that they got explanations for where the score was really good. So out of all the neuron, you're kind of just matching this one explanation with one neuron, and then it's only 1,000 out of how many, hundreds of millions, I think billion parameters, that they have explanations for. So it's a pretty much smaller set of neurons in the full set that had the activation level high enough to even make the explanation set.
Yeah, if I recall correctly, their criteria for even like publishing the results was that it was better than like human labelers, and that was it. It like beat that bar, which is like, okay.
Yeah.
It did like a very statistically significant.
But like, I think, I don't know, I
outcome.
feel like the underlying assumption here is like a neuron maps to a concept. And I
Yeah.
don't think that's how it works, because a neuron maps to, it's like you took everything into a blender and then blended it up, and it's like it doesn't, the assumption is wrong, because it's neurons don't map to a concept, they map to like a huge amount of things, right? And there's no way, I don't know, I call bull hunky, but
I think though there's a chance to make this work in the vector space, embedding space, because like in there you have things working together to you basically when you're training, you're kind of minimizing errors, and that those are just have to map to surfaces, but it still might not be like, it might be a complex set of subjects, it might be multiple things it means, like there's just so many things, but going to the neuron level, I think you're exactly right.
And I think they say that in the
Yeah.
limitation, they said neurons may represent many features, right? It may not correspond to a single semantic concept of ing verbs or community. And honestly, if you look at some of what they lit up on, let's go over here. It's actually pretty, I mean, I can't figure out a single way to explain. Let's go to introduction. like the things that the neuron lit up on, best, keep, tied, better, think of, like it doesn't feel like there's a single semantic concept that you can go and, when we look at our embeddings and we could say, oh, generally this represents this. I feel like it's really hard to do that. When I just even looking through a couple of these, it's really hard to think of one semantic concept. And then the simulated activation, I feel like it's trying to just focus on that one semantic concept, and it misses all the stuff that the real neuron actually does.
Wouldn't it be better? Like, I thought this is how they work, but it's like the abstraction was like, if you go to the encoder decoder layer, like that's a higher level. And it's like, maybe this encoder decoder is looking for parts of speech, or this one's looking for semantic meaning and blah, blah, blah. I don't know. I feel like they went too low on this one, but it's like, just go one step up. And I don't know. It would be cool to see them do the same thing one layer up.
Yeah,
Yeah.
they did do some analysis layer wise, like at different layers, but like I still think as you go deep in it, I mean, some of the results got worse, some got better depending upon what you're measuring.
Yeah, I'm trying to find, there was a part where it said, I think they said only 86 or something out of all of the example real versus simulated even got a score of above 0.03. So it's a really small set of these simulations that got a
Yeah.
or that actually meant something. Yeah, meant something that the simulated neurons could even try to be close to the real.
So I'm ripping, but these guys are honestly way smarter than me. But so I'm just to be fair to them.
I'm surprised they put as much into this. I mean, maybe, I mean, I think using AI to evaluate AI is definitely important. And like, definitely is going to be a valuable thing, but it's a lot of work here for a direction that feels hard to think it will pan out. I don't know, but they are way smarter than me as well. So I don't want to, there's something they're working on here.
Yep. And I mean, what else is worth highlighting? I think they spent a fair amount of time just talking about, well, how they were evaluating these results. And this felt shaky to me too. They tried to use random documents and they got really bad scores on random documents. And so then they used top and random and got slightly better results. And so they always have kind of the random scoring versus the top and random. And that felt, I get what they were getting at, which is you want to pick the subset of tokens where you're getting the highest activations instead of just random tokens, but it did a really hard time. It had a really hard time mapping to other documents that they showed it. So that felt kind of shaky too.
And if you go down a little further, I think the other thing was really, if you just page down a little bit here, there's a section, keep going there. They talk about the false positive right here. I thought this was kind of the least, it was the most telling, where in practice, roughly 42% of the sequences resulted in false positives, and 86% of the neurons, at least one of the 10 sequences result in false. I mean, it's just like, is it really, it's working, but just not that often. And what's it telling you? Like, that this was the one where I was most skeptical when I got here. It's pretty bad. And then a lot of it's trying to fix. Then the next section, I feel like it's trying to fix that a bit.
Yeah. Yep. I mean, maybe this is a question for you all, but do you guys, what would be the application for having explainable LLMs? Like, what would you, if an LLM gave you a perfect response or incorrect response, would you want to understand how did it come up with that? What's the use case for explainability here?
I think they mentioned alignment, just to spot when it's going to do stuff that's deceptive, stuff like that. I
Yeah.
don't know what you would then do. You'd either kill those neurons or I don't know.
Yeah. Yeah.
Yeah, I think that's a good one. So understanding internally if the thing is not doing what you want it to be doing. I think there's kind of that's probably a big one. So just making sure, you know, look internally to make sure that the model is actually doing what you want it to be doing. Probably the second one is going to be what I would say, and it's harder and less likely, but imagine there's a dream that like you understand these enough that like when you see a problem, a specific hallucination or a specific output that is wrong, it does this step-by-step, you know, chain of thought, and it's all right, and then it gets the wrong answer at the very end. Like why and what would you do, like giving you some inclination of what to go fix, either in the training data or how to fix it. Like that's kind of the dream. Like it's kind of those two, what's going on internally for production or monitoring, and then maybe it's like improvement on through that. But we feel pretty far away from, really far away from the second one.
Yeah. They did hint at, I think in a section here about using, I mean, fundamentally using the embeddings.
Mm.
Do you guys catch that?
Yeah, I think we'll see it. I mean, the next version of this, hopefully they do that. I think it will start to be more
Yeah,
a more solid long-term
fundamentally,
direction.
fundamentally, these techniques depend on multiplying the input or output weights of a neuron by either the embedding or unembedding matrix. So I do feel like, yeah, the next version of this might dig into embeddings. Cool.
Anything else anyone wants to add?
I do think the interesting neuron section, they did find some stuff, unless it was randomly hit. Where
It's absolutely, I think you're right, Darren. I mean, I think there's absolutely neurons within GPT-2 that map very specifically to an idea or concept. Like I'm sure there's activations in there that map one for one, or not one for one, but pretty close to certain ideas. And there might be a lot of them.
like at the bottom on the left side, they have qualitative results, interesting neurons.
Yeah.
They get into this one's where the concept changes. So it's like they're giving countries, and then suddenly there's a word that's completely different, and it seems to always be when the concept changes. But yeah.
An interesting example of a polysemantic neuron is a neuron that fires for both the phrase over and over again and things repeated right before a non-repeated number, possibly because over and over itself includes a repetition. So that's pretty interesting. I thought the concept of a polysemantic neuron was interesting.
Yeah, and there's actually quite a good write-up by Anthropic that that goes through a similar thing here, and shows pretty clearly like you might get a neuron activated for one idea, but that same neuron could activate for something completely different in a different scenario, almost like tangential. So the idea that like you get many features overlapping into one activation, one place for activation is it's kind of real.
Yeah.
It's just hard to like look at the stuff. Yeah.
Yep. They had, I guess, I know we've been ripping on it, but they do have like in the interesting neurons, just a set that they felt like was well explained by GPT-4, and then a set that maybe explained and then really badly explained. And so something like similes, this was cool to see. Water mixed with water, they go together. It's like choosing between black, so like there's kind of certain one of these that I thought it actually, if you go and you look at it, got higher scores than the rest, but overall it did feel like it was really hard to have a lot of takeaways from this right now.
Cool. Well, I feel like this discussion was better than the discussions I saw on Twitter, for what it's worth. Awesome.
Well, anyone else have anything else to say or comment on, Michael or Mickey? I feel like you guys were also looking at the paper.
Can I just ask something that's going to demonstrate my complete ignorance of of the topic? But when I think of a neuron in biology, right, axons, dendrites, and thousands of connections going into and input and output from one nerve cell, right? In artificial neuron, like how many concurrent connections can go into one neuron at one point? And theoretically, if we can increase that number, right, that would be a complete game changer, wouldn't it?
I think in the concept of this paper, Jim, what they're trying to do is almost explain this neuron. You just imagine in your brain when you hear, I don't know, there's like certain neurons when you like think about math or when you think about TV shows, they get activated. I think what they were trying to think about was like, is there a one-to-one mapping between some concept and maybe what neurons get activated? And so it's actually, I feel like the opposite of what you said, which is one neuron can handle more concepts. They're trying to, in the world of it getting to be more explainable, trying to have it represent a single concept. And I feel like one of the things they themselves pointed out at the end is that it might not be true. A neuron might represent more than one concept. And so it's hard to know what makes a single neuron activate here.
Yeah.
Does that answer your question?
And then the general, what we're seeing, I guess, when you talk about like your concept of just connectivity and connections, like I would say transformers are kind of going in opposite direction, where like the architecture matters a lot more than like a really dense, deep, recursive network of connections and things all flowing through to each other. So the move has been like architecting the structure of things differently instead of trying to get more connectivity, like your example was talking about.
Got it. Thanks.
Yep. Cool. Awesome.
In terms of the overall approach, one thing that came to mind to me as a question is like, if you're using the fourth generation to explain the second generation. So I don't question the value of being able to explain the output, but it seems like you'd want to be able to explain the output of the most powerful one too. So just like the strategy.
Yeah,
I'm not sure how it ends up working
it's a good point.
iteratively.
You got to wait for GPT-5 to explain GPT-4 now.
Yeah, totally get it. Especially if you're trying to deal with like alignment and making sure things are working correctly.
Presumably, if you have some mission critical task, you're not using the second generation, you're using the fourth generation. So
yeah,
the explainer can't help you.
Yep.
Transformers all the way down, I guess.
Cool. Well, that was fun. All right, everyone.
Awesome. Thanks, everyone. See ya.
Ciao.
Thanks, Aparna. Bye.